In Module 5, we didn't quite finish the questions together in class, so this is my second attempt here at getting you a video that will demonstrate how to complete the problems. So we are first looking at problem number 16. 16 asked us to calculate the mass of H2 that is present in an ideal gas mixture. The key components here is they're giving us standard temperature and standard pressure. They're giving it to us in torr, but it equals 1 atm. And if you can remember that at STP, 1 mole of gas takes up 22.4 liters. So we know we're looking for 1 mole of gas total. So we're going to do some quick conversions here. They give us 11 grams of CO2. We convert that into moles. We're dealing with 0.25 moles of CO2. We're also dealing with 8 grams of O2, so we're going to convert that into moles as well. One more thing to consider here is we are down to just 1 sig fig due to that 8 grams of O2. Anyway, we get 2.5 moles of O2. And so we are so far dealing with half of a mole of gas. We know that we would have, based on 22.4 liters, we know that we'd have a total of 1 mole of gas. So we could just simply say we have a half of a mole of H2 and then calculate and turn that into grams. However, we can also show it using the ideal gas law. So if we were looking for volume, we could set PivNerd up to solve for volume. In this case, we're really looking for moles because we are given a volume, we are given pressure, we are given a temperature. So we're going to calculate for total moles. We plug in our pressure. Let's go ahead and just convert that to our 1 atm. Our volume we're given is 22.4 liters. Rate 0.08206, or most common here 0.0821. So we'll just keep using 0.0821. And our temperature is 273.15 Kelvin. That's going to give us 1 mole. So now we know that we've used 0.25 moles of CO2 and 0.25 moles of O2. So what is left is we have 0.5 moles. And again, we are down to just 1 sig fig thanks to that 8 grams of O2. So 0.5 moles of H2. It's asking for us to convert that into grams. So we take our 0.5 moles times 2.02 grams per 1 mole of H2. And we're left with 1.01 grams. But the real answer should be 1 gram of H2 due to that sig fig limitation. So 1 gram H2 is the more accurate answer. 17, we are given pressure on 525 cubic centimeters or 525 milliliters of helium gas is increased from 2 atms to 3 atms. So far they've given me a pressure, they've given me a volume 1, a pressure 1 and a pressure 2 and a volume 1. So they are asking me to calculate volume 2. So I'm going to list out my numbers here. Think back to PivNerd. And so I know that PV go next to each other, so I can use P1V1 equals P2V2, and then plug in my numbers and calculate. So we have our 2 atms and our 525 milliliters. We're solving for volume 2 at 3 atms. We only have 1 sig fig here. So we have 0.350 milliliters. A more accurate answer would have had us round that to 0.4, or a more correct answer thanks to sig figs. But that's how the math works out, so we want to show that in completion just in case we would have had more sig figs. Next, how many liters of hydrogen measured at standard temperature and pressure would be produced from 2.7 grams of aluminum? And so we start out by using pivnert. We want to calculate how many liters or volume, and so we'll plug in our numbers. 0.0821, it's STP, so 0 degrees Celsius, so 273.15 Kelvin. And then I need to know N, or moles, but I'm given grams. So I'm going to type in my 2.7 grams of aluminum times 1 mole is 26.98 grams. All over P, and it's STP, standard temperature and pressure, so it's just 1 ATM. So I'm going to calculate volume, and I get 2.2 liters. And then we'll move on to 19. And this is similar to one of the labs that we are looking at with Hess's law. But we are looking to calculate the molar mass of an ideal gas, which has a density of 1.87 grams per liter at 30 degrees Celsius and a pressure of 0.9 ATMs. So we are looking for molar mass. That's grams per mole. And so we need to first solve for moles. So we're going to set up our pivnert equation. We can later use the density to calculate what we want in grams. We're going to assume a 1 liter sample here. And if we had a 1 liter sample of volume, our total moles are 0.04. So now that we know that we are working with 0.04 moles, we can utilize our density. Remember, we were using grams per liter, and we were working with a assumption of a 1 liter volume. And so if we would have had just 1 liter of this substance, it would have provided us with 0.04 moles. However, according to density, that same liter also has a mass of 1.87 grams. And so now we can calculate our 0.04 moles has a mass of 1.87 grams. And again, molar mass is grams per mole. So we're going to set that up. Let's convert it to 1 mole, would have had 46.75 grams. And again, a more accurate answer would be 46.8 grams per mole, thanks to sig figs. Problem 20 is just which gas diffuses the most rapidly. And so gases will diffuse at different rates based solely on their molecular weight, so long as everything else is consistent here. And so we're going to calculate the molar mass of each of these gases. Neon, 20.2 grams per mole. O2, 32 grams per mole. Ammonia, 17.03 grams per mole. SO2, 64 grams per mole. So the one that has the least mass per mole would diffuse the quickest. Takes a little bit less energy to move it. That brings us to 21. We have our balanced net ionic equation here, and this is also similar to a lab that we've done in class. We are looking at a gram sample of zinc. You used magnesium in the lab. Is added to excess hydrochloric acid. When the reaction is complete, what volume of gas in milliliters at STP was evolved by the metal sample? So we're working with a 0.10 gram sample of zinc. We'll get the molar mass of zinc, 65.4 grams per mole. We're going to use our mole to mole ratio. And again, we would be looking at the net ionic equation here. So zinc is going to go from zinc 1 to zinc 2, as you'll see over there, when we balance out our total equation. So we do our mole to mole ratio, and we're going to end up with 1 mole of zinc per 1 mole of H2. And since I'm being asked for the volume of gas in milliliters, I need to get out of moles of H2 and into liters. So I know it's 22.4 liters per mole at STP. And then I get out of liters and into milliliters. We multiply across and divide by the bottom. And we get 17 liters. And this is correct to two significant figures.